Welcome back to ECE 320A. Homework number 4 is due today. Homework number 5 is due in a week. And the exam is a week from Thursday. So that you don't have to worry about studying for 320A maybe over spring break. Isn't spring break the following week? You wouldn't mind? Okay, well, we're trying to get you ready for final exam period for all of the different exams. Today what I want to do is cover material that you can find in section 7 of chapter 12, which is on inverse Laplace transforms. To perform the inverse Laplace transform with rational expressions, rational in S, that just means you have polynomials in S in the denominator and the numerator. That gives you a rational expression or a rational function or what may be a transfer function or just a transform. The textbook talks about a proper transform. I try to be a little bit more specific and call it a strictly proper transfer function or a transform, and we'll try to get into that as we progress through today's lecture. Actually, that's the first thing that we need a proper or strictly proper transfer function or transform to perform the inverse operation. And then I'm simply going to break it up into two pieces or two different cases. One case is when all of the roots are independent, meaning they are not repeated. You have a root at -1, there's no other root at -1 in the denominator polynomial. Or I might call it a simple root, meaning you might have a complex pole at -2 plus and minus j3, and if that's the only pole at that location, it would be simple or distinct. And the case 2 is when you actually have repeated roots or multiple poles at one location. If you had now a pole at -2, another pole at -2, and a pole at -3, -3 would be a simple or distinct root, -2 would be a repeated root. Hopefully that will start to make sense as we go through this material. Let's get started. Again, this is section 7 in chapter 12, and hopefully it's clear why we want to be able to do this. We now are going to be able to solve circuit problems in the frequency domain, and we will end up with expressions for voltages and currents that are Laplace transforms of those quantities, and we want to get it back into the time domain, meaning we need to obtain the inverse Laplace transform of all of these expressions. As I said, we'll try to represent this or break this down into two cases. And all of these cases, two, it's not that many, so two cases, all of those cases pertain to the denominator polynomial. In this discussion, I may start talking about roots p sub I, and p sub I is just an indexed variable, index being little I. That's not the complex number square root of -1, that's an index I, and p sub I can be either real or complex. Just keep that in mind when we're talking about this. Here are the two cases that I had suggested. The textbook calls them distinct roots, but I may call them simple. So those are interchangeable descriptions of the roots. Again, these are either real or complex. And we might write that as an example, some numerator polynomial n sub 1 of s is simply a polynomial in s, and it's going to be generic. And then we have these simple factors, s plus p1, s plus p sub 2, and s plus p sub 3. In this example, what's the order of our denominator polynomial? Oh, I'm sorry. I thought I was in a class full of students. I didn't hear anything. 3. Okay, so that was pretty easy, I think. That's a third order polynomial. And for distinct roots, we do not want p1, p2, and p3 to be equal. And if p sub 2 is complex, p sub 3 or p sub 1 would be its conjugate. And those are considered distinct or simple. The fact that they're paired up, that's okay, but if you plotted those in the complex S-plane, they would not lie on top of each other. One would be in the upper half S-plane, the other would be its twin or mirror image in the bottom half of the complex S-plane, and those would then constitute distinct roots. The other case that we will identify when we're inverse Laplace transforming is just the opposite, or maybe I should say the complement of when we have simple or distinct poles. Now we have repeated roots, and these likewise can be real or complex. And in this case, we could say, oh, here's an example. And little n, let's say, is bigger than 1. And if that's the case, then we have n roots at s equal minus p. They're stacked on top of each other. Those are the two cases that we want to address or identify and keep track of. And the first thing that I want to discuss is the fact that in order to do these inverse Laplace transforms, there needs to be a particular property relating the numerator polynomial and the denominator polynomial. And in particular, the degree or the order of the numerator polynomial needs to be strictly less than the degree of the denominator polynomial. So that's this star that I'm trying to identify. Before performing an inverse transformation or an inverse Laplace transform, the degree or order of the numerator must be less than the degree of the denominator polynomial. As I said before, I may call this strictly proper. The textbook may just call it proper. And the other is just the opposite. If you have a numerator polynomial that is equal to the denominator polynomial, I usually call that proper, but the textbook lumps that in with the case where the numerator polynomial does exceed in its order the denominator polynomial, and they just call those improper transforms, or in the case, as the case may be, transfer function. Let's look at an example. Suppose that somebody gives us a transform, f of s, that's s to the fourth plus 3s squared plus 2, and downstairs you have two factors, s plus 1 and s plus 2. And maybe you need to put it all together so that you can compare. Now that you've multiplied out the denominator polynomial, typically we want it factored, but what's the degree of the numerator? And also, what's the degree of the denominator? What's the degree of the numerator? 4. So this should be fairly straightforward. In the denominator, we can't directly inverse Laplace transform that quantity. We need to basically do it in two steps. We first need to identify or divide out the numerator polynomial in such a way that we've created a numerator polynomial that is strictly less in degree than the denominator polynomial. And we can do that if you remember I'm not sure where you learned it. First grade or second grade, where you learned long division. So now you have long division. What am I looking for? I'm looking to rewrite f of s as, well, what would I expect? If I performed long division on f of s, what's the first result of that division operation? What term am I going to see first? An s squared term. Because the denominator is exceeded, the numerator exceeds the denominator by 2, so we expect to see something times s squared plus something else times s plus something, which is, we could say, a constant, or we could emphasize the fact that it's s to the 0, which is just a constant. And now we end up with what we want or need, which is this f, let's say, sub 1. Maybe I should have called it the numerator, sub 1, over the original denominator. And these terms are found from long division. And does everybody remember how to do long division? Not even synthetic division. Now we do long division. We had our numerator, which was s to the fourth, and I've made this a little more interesting because I'm not including all of the powers of s that could potentially be there, but I'm going to now divide that numerator by the denominator, which is s squared plus 3s plus 2. And my numerator originally looked like 3s squared, so I don't have anything with the cubed, and I don't have anything with s to the 1. That's now my numerator polynomial, written to sort of leave space or gaps where I know that there's another power of s that's actually missing. And to perform this, I simply do it like we do most of our division problems. I have an s squared will go into s to the fourth by s squared, and now I simply multiply my denominator by that s squared, and I have s to the fourth plus 3s cubed plus 2s squared. And now what I'm trying to do is start reducing the remainder's order, or the order of the remainder. The s to the fourth does that for me, and now I subtract 3s cubed from nothing, and I subtract 2s squared from 3s squared, and end up with the following remainder. Now I need to divide my denominator into that remainder, minus 3s cubed plus plus s squared. What's my next quotient term? I need to make the powers of s the same, and now I have minus 3s times s squared, which will give me what I need for the first term. Now I have a minus 3s cubed minus 9s squared minus 6s. Questions on what I'm doing? It's not hard, it's just time consuming. Stuff you did a long time ago, which means what? It's easy, or it's pulling back stuff that you are having a hard time remembering. Flashbacks to your third grade teacher, huh? Now what do we have? Oh, I need to subtract these. Am I finished yet? I'm actually looking to make sure that the denominator, or the remainder, I need this remainder polynomial to have an order less than the denominator polynomial that we started with. And so I'm not done yet. I still have to keep going in this long division process. And I can finish it up by seeing that a 10 times s squared will give me the first, or the leading term in that remainder polynomial. And now I have to simply multiply everything by 10. And my remainder now is minus 24s minus 18. And that's the remainder I can work with to perform my inverse Laplace transform. I can now write f of s as whatever I just had, s squared minus 3s plus 10 plus a minus 24s minus 18 all over either this s plus 1, s plus 2, or its multiplied out quadratic form, s squared plus 3s plus 2. Questions on that? Where did the 10 come from? Did it sneak? So the 10 came from, I had this as a remainder, and now what I'm wanting to do is, I know that I've highlighted in yellow has the same order as my denominator polynomial, and I need to get it one more lower in degree. So now what I need to do is I need to multiply my denominator by 10 and take that away from that remainder. Doing that leaves me with this minus 24s minus 18. Does that make sense? Now, what I want to do is well, maybe this will be a good time for class participation. I would like to know what kind of calculators you guys have, actually, because your TI-89 will do this for you. Really? So take out your calculator if you have one and see if you can make this happen. The command that you want to use is this proper fraction. So now if you do the proper fraction, I would like to know, just to see how much time I want to spend on this. I may not spend class time, but I might make some little videos or something to help explain how you can do these on your calculators a little bit more time efficiently. If you know the process, all you have to do now is sort of plug it in and let the calculator do the hard work for you. That's the idea. But that's then what you would do. In this case, a lot of times I like to put my formulas in terms of x's, just because s, I'd have to do a second something on that. So I might say something like x raised to the fourth plus, what was my polynomial? 3x squared. Is this making any sense? Plus 2. And then I would divide that by the denominator, which was x caret squared plus 3x plus 2. And hopefully that would give me the correct answer. Pardon? It'll do the whole thing for you. No, I don't think it actually asked you to get, so the question was, do you have to put x in as like a comma x? You don't have to. You actually want it to work as if x is a variable. So x, that's not the multiplication symbol. That's x raised to the fourth plus 3 times x. And I don't think you have to put the times in there. I think it's algebra is okay. So you have 3x squared plus 2, all divided by x squared plus 3x plus 2. I'm sorry? What do I want on your class participation? I would like your name so that you get credit for it, and your calculator that you have or have available to you. Whether you have a TI-83, a TI-84, a TI-89, a TI-89 titanium, if you have an HP, etc. What, HP? All right, so now that we have that, what we want to do is actually inverse Laplace transform capital F of S. So I don't really need you to give me the answer. I hope I've done the long division right, but that's a good way to check on your in-class participation. All I need is your name so far, and maybe I'll have some other important information that you put on that sheet also to turn in. What we're wanting to do, yes, put your Social Security number on there, bank account, password for that account, etc. F of t, but we won't record all of that. You can just record it on your paper. Little f of t is what we want, which is the inverse Laplace transform of capital F of s, which says now that we need to inverse Laplace transform s squared a minus 3 inverse Laplace transform of s plus a 10 times the inverse Laplace transform of 1 plus the inverse Laplace transform of minus 24s minus 18 all over s plus 1, s plus 2. And that's what we want to find to obtain our time domain expression, or our time domain signal, f of t. What I want you to keep in mind is f of t is a signal or a waveform as a function of time t. That means that all of these other things need to be signals that we're adding up. This result needs to be a signal. This result needs to be a signal. This needs to be a signal, as does that. All of those pieces have to be signals, and we're adding them up to get the result, little f of t. And now we need to figure out how do we go from frequency domain, which is this s, or 1, or s squared. We're going to spend most of our time actually on that lower right-hand term, which is a strictly proper or a proper transfer function or transform, where the numerator order is strictly less than the denominator order. But we need to figure out how do we treat these other pieces that have appeared or now show up because of this improper transfer or transform that we started with. Let's start maybe with we've already learned some transform pairs, hopefully. And what was the Laplace transform? So now you have to make sure that I'm either saying Laplace transform or inverse Laplace transform. Right now I'm saying Laplace transform. What happened when we Laplace transformed the impulse? What was the Laplace transform of an impulse? That was the sifting property, wasn't it? And we evaluated the integrand when that impulse occurred, which was right at the origin in time, and that gave us 1 for our answer. That's a transform pair. Well, if that's a transform pair, then we know how to invert that pair. Meaning, if I now invert both sides, I can now say the inverse Laplace transform of 1. So if I ended up with 1 in the frequency domain, that in the time domain is an impulse. Is that making sense? Now I'm just going the other direction. Meaning if I operated on the top equation on both right and left-hand sides with this inverse Laplace, I would end up with a delta of t equal to the inverse Laplace of 1. That means that in the frequency domain we have a constant signal, and if we take that back in, so in one way of thinking of it, you have all frequencies present in that signal because your frequency response says it's constant for all frequencies. It's 1. That says that your impulse as a signal excites all frequencies in your system. That's sort of one way of interpreting that. But here all we really have to know is that the inverse Laplace transform of a constant is going to give us a weighted impulse function. Now we can start doing that in steps. What if I now wanted the Laplace transform of the derivative of an impulse? If you thought the impulse was a weird function, it's a generalized function. Now we're taking the derivative of it. Whew. So now what that looks like, well, what you could maybe do is you could say, okay, let's approximate the impulse, and then what would that look like if I differentiated it? If you just had a really sharp TP, that's maybe an impulse where the width of that TP is infinitesimal and the height is infinite. But now you can sort of say, oh, what would happen if I differentiated that? And you can kind of see what's happening or could be happening in the time domain. But here we're just wanting to do this from our definition of Laplace. How do we Laplace transform a derivative? S times the Laplace transform of the waveform that's not been differentiated, which in this case is the derivative, which is the impulse, minus the function that's not been differentiated, evaluated at, and now you need to make sure that minus is on your 0, of delta of 0 minus. That's just the definition of our Laplace transform of a derivative. And what can we do with this? What do we know the impulse is equal to at time t equals 0 minus? It's nothing, right? At 0, just to the left of the origin, it's nothing. So that piece goes away. And what's the Laplace transform of an impulse? 1. So now we have s times 1 minus 0, or we just have s. And hopefully you can see what I want to do now. Now we have a transform pair. We know the Laplace transform of the derivative of an impulse gives us in the frequency domain an s. If we now inverse Laplace transform s, what does that give us in the time domain? The derivative of the impulse. And now let's do that one more time. Now if we Laplace transform the second derivative of an impulse, this is now s times the Laplace transform of the derivative of an impulse minus the derivative's value at 0 minus. And what do you think this looks like? We just calculated the Laplace of the impulse as derivative, and that was s. So now we have s times s, and what's the time rate of change of the impulse at 0 minus? 0. It was not doing anything at that location, so it's 0. And now we have the Laplace transform of the second derivative of the impulse is s squared, or we can now say that the inverse Laplace of s squared is the second derivative of the impulse. What in the world? So what do we have? Actually, that allows us to write down the first few pieces of our time domain waveform f of t, if that really even makes much sense. But what do we know we have? If we go back, the very first term was supposed to be the inverse Laplace transform of s squared. We just derived that. What does that give us in the time domain? The second derivative of the impulse. So now we have impulse differentiated twice. What's the next term in that f of t, little f of t expression? Question? So now the question was, how specific or detailed do I want to factor my argument, I think, is the question. In this case, I just have s by itself. I factored out the coefficient of -3. I could have said, oh, I want to have the inverse Laplace of -3s. That's okay. That would just have been -3 times whatever the inverse Laplace of s is. But if I say, oh, there's a 1 in there, that 1 as a coefficient can actually be factored out and combined with the -3 and keep it at -3. So that's not really telling us any new, it's not adding or introducing any new information. Does everybody understand what we're trying to do? We have these extra pieces, which in most physical systems we're not going to have this, but I just want you to know that it is a possibility on an exam. If you now have an improper transform, how to deal with it, how to compute its inverse, Laplace. What's the next term in our expression for little f of t? We have minus 3 times the inverse Laplace of s plus 10 times the inverse Laplace of 1. The inverse Laplace of 1 was the impulse. So we have 10 weighting the impulse. And finally, then, we have plus the inverse Laplace transform of minus 24s minus 18 all over s plus 1, s plus 2. And that's really what we want to concentrate on now. Now that we know how to compute or deal with improper transforms, we can now concentrate on the proper part of that transform. And that's what's left to be inverse Laplace transform. Questions on that? Now what we want to do is perform partial fraction expansion on that proper transform. And the partial fraction expansion, one thing to keep in mind is that that expression is true or valid for all values of the complex frequency variable s. And that will make sense maybe when we start evaluating or trying to find the partial fraction expansion coefficients. Let's look at some cases. Let's say case 1, which is when we have distinct roots. And again, the roots can be either real or complex as long as they are distinct. Suppose our f of s, is that going to confuse you if I use capital F of s for new things now? It's not the same as what I just finished talking about. Capital F of s, let's say, is now this n sub 1 of s over s plus p1, s plus p sub 2, and s plus p sub 3. And we are already assuming that the degree of n sub 1 is less than 3 for this example. This is a proper transform. The partial fraction expansion for f of s is now going to be some coefficient, I'll say a1 over s plus p1 plus an a sub 2 over s plus p sub 2 plus an a sub 3 over s plus p sub 3. And that's how we will rewrite f of s, because we know how to now inverse Laplace transform these individual terms. That's what we're wanting to do. We want to factor this in such a way that we can now go immediately into the time domain from these expressions. And all we need then are these coefficients. We need a1, a sub 2, and a sub 3. And the method that's easiest to do, actually, is to simply multiply both sides. If we want to solve for a sub 1, we would multiply all the terms, or both sides of the equation, f of s and the right-hand side, we would multiply all terms by the factor s plus p sub 1. And then we would evaluate both sides when s was equal to the value that makes that factor vanish, or when s is equal to minus p sub 1. Written down, that simply says that each of these coefficients, a sub I, can be found by taking its associated factor, multiplying it by the left-hand piece or expression, and evaluating that expression when that factor s plus p sub I is 0. That's the method that we can use when we have simple or distinct terms in our partial fraction expansion. Let's just illustrate why that works. Suppose we have this f of s, and I'm now going to multiply it by s plus p1. And when I multiply the right-hand piece, or let me just say this is now what happens when I multiply f of s times s plus p1, the numerator stays the same, but now I've canceled that factor from the denominator. That's what I've done effectively. And now that needs to equal a1, which when hit by s plus p1, those two factors cancel, and all I am left with is the coefficient I'm trying to evaluate for, which is a sub 1. Then on the other pieces, I have this a sub 2 times s plus p1 over s plus p2, and I have a sub 3 s plus p1 over s plus p sub 3. And what I want to do now is evaluate this meaning that left term has become changed to the second piece in that expression, and so it's not going to vanish necessarily. It depends on what n sub 1 of s does when you replace s with minus p1. But now a1 is just going to be there, but what happens to this piece? It's going to be forced to 0. Likewise, for the last term in that partial fraction expansion, it likewise vanishes, and that's why I now just have the a1 available to me. So that now a1 ends up being this n sub 1 of s over s plus p sub 2, s plus p sub 3, evaluated at the value of s equal to minus p sub 1. Let's look at a specific example. Hopefully that helps you understand why this isolates each of those three coefficients in this case, a sub 1, a sub 2, and a sub 3. Let's now look at a function 2s squared plus s plus 4 all over s plus 1 and s plus 2 squared plus 3 squared. Am I in case 1? what are the roots of my denominator, or where are my poles? The easy pole, or how am I now going to rewrite this? I'm now going to rewrite f of s if I now consider are my poles distinct, and where are they? I have a pole at -1. And the other is actually a complex conjugate pair, isn't it? And it's only one, it's a quadratic, and those roots are at -2 plus and minus j3. Those are distinct, and so I do have case number 1. My partial fraction expansion will be, depending on how you put this together, let me associate a sub 1 with the first term, and then I'm going to have an a sub 2, and this one I want its Is it clear where that pole is located? It's where that factor vanishes, the value of s. That's at -1. Where is the pole located for this second term? And the reason I'm going through this is because it's important to find a sub 2 and a sub 3. Where is this pole located? This one is actually -2 plus j3. That's in the upper half. And this one is at the lower half. Those are the values of s that cause that factor to become 0 or to vanish. Simply plug in this value for s, and hopefully the pieces all cancel and you're left with nothing. Is that making sense? Those are where our poles are located. So a sub 2, this is important in the formulas. A sub 2 will be associated with the complex pole pair that's in the positive half of the s-plane, the positive top half of the complex s-plane. And that's the one that we key on. What if we want to find A1? A1, so now we have a steak, and we want to find the sauce. A1 steak sauce. Nobody, oh, sorry. Sorry. Well, you guys were starting to drift off, and I needed to kind of wake you back up. So we now have A1 that we are trying to find, and we said multiply through by s plus 1, everything, and then evaluate at s equal to -1. The numerator is not going to change, or I now have this 2s squared plus s plus 4, and in the bottom, I've canceled my s plus 1 factor, and now I simply need to evaluate that at that pole location of s equal to -1. Or A1 now becomes 6 minus 1, is that right? Or 5. And downstairs I have 1 squared plus 3 squared, or 10. Or A1 now becomes 1/2. That's now my partial fraction expansion term associated with the factor, or the pole factor, s plus 1. Questions on that? What about a sub 2? The numerator is going to be the same in terms of its structure. What's the denominator look like? I have not eliminated the s plus 1 factor because now I'm multiplying through by which factor? The factor associated with a sub 2. What you need to recognize is that now this square bracketed polynomial in the denominator for capital F of s, the s plus 2 squared plus 3 squared, is equivalently written as the product of s plus 2 minus j3 times the factor s plus 2 plus j3. And now I'm multiplying that through by the s plus 2 minus j3. That piece goes away. And I'm left with, in the denominator, not only the s plus 1, but the s plus 2 plus j3 piece. And where do I evaluate this? At the pole location that I'm interested in, and that's why we said it was important to know which one went where. That was the pole at minus 2 plus j3. And now we simply plug in s as that complex number. A sub 2 is now 2 times minus 2 plus j3 squared plus minus 2 plus j3 plus 4 all over minus 2 plus j3 plus 1, and we have minus 2 plus j3 plus 2 plus j3. And if you perform the algebra, you end up with minus 8 minus j21 over minus 18 minus j6, which if we wanted to take the ratio of two complex numbers, we might put it in polar form. Where's the angle of the numerator? Or where's the angle of the denominator? They're both in the same quadrant, aren't they? They're both in the negative real direction and negative imaginary direction. They're both in the third quadrant. This one actually ends up being at a length of about 22.5 at an angle of minus 110. This one is 18.97 at an angle of minus 161.6 degrees. Or a sub 2 is equal to 1.184 at an angle of 50.8 degrees, roughly. So now the question is, what is a sub 3, I think is the question. Actually, the question was leading even further than that. It was saying, is a sub 3 the conjugate of a sub 2? And the answer is yes. You've basically found a sub 3. All you have to do now to find a sub 3, if I tell you a sub 3 is the conjugate of a sub 2, how do you find a sub 3? Just negate the angle. So now we know that a sub 3, if we actually wanted to compute it, and maybe you should do this tonight because you'll just want to prove this to yourself. What's the formula here? It's 2s squared plus s plus 4 all over s plus 1. And what factor do we have now in the denominator? It's the s plus 2 minus j3. You evaluate this at what value of s? Now you're in the negative, or the bottom half of the complex S-plane. You're at -2 minus J3, and you should find that this ends up being the conjugate of A sub 2, which in polar form is just the same magnitude, just the negative angle. Now we're in a position to try to put this into a form that allows us to go back into the time domain. We now have capital F of S is equal to this 1/2 over S plus 1, and we have 1.184 at an angle of 50.8 degrees over S plus 2 minus J3 plus 1.184 at an angle of minus 50.8 degrees over S plus 2 plus J3. That's the partial fraction expansion of capital F of S. What's the time domain waveform associated with that transform? What's the first piece of that? Now we simply have to inverse Laplace transform 1 over S plus 1. And where is that pole? It's at -1, and what does it look like in the time domain? That's a decaying exponential with the exponent of the 1. So now we have this 1/2 e to the minus t. Now what's the next term look like? If you just needed to qualitatively explain this to somebody, once you have these complex poles, what do you know they look like in the time domain? Decaying sinusoids. What are the frequencies of those? What's the damped frequency? And we'll try to get a little bit more detailed about this. What's the damped frequency of that sine or cosine? The imaginary part gives us the damped frequency, which is 3 radians per second. That's how quickly, that's the omega. It's now cosine of 3t or sine of 3t. And what's the exponential damping? How far into the left half plane are we? We're at -2, aren't we? That gives us this e to the minus 2t cosine 3t, or an e to the minus 2t sine of 3t. Those are the terms that we would expect popping out of something like that. But in this case, if we simply apply the formula that we've just applied, we could say, oh, that was e to the pole location -2 plus J3 times t. That's e to the p sub 2t. Just like the first one was e to the p sub 1t, where p sub 1 was -1. And now we have the other piece, which is plus 1.184 at an angle of minus 50.8 degrees, e to the -2 minus J3t. Questions on that so far? That's really not looking like a sine and a cosine, is it? Which S are we referring to? Oh, this S here? So now that S, the question was, doesn't that S correspond to a unit step? When would, and now I need to somehow cover things up, and I can't cover things up on a tablet. If I had this on an Elmo, I could just cover things up. If you put your hand over the 1, I can cover it up for the live audience. And now just call 911 if I fall. But no, don't call 911, please. If I cover this up, there's your unit step in the time domain, isn't it? But now what is it? It's no longer a unit step. It's now replacing the s with this s plus 1. And what did we learn about replacing s's with s plus a's? In the time domain, that scales that unit step with an e to the minus at. So now we have that waveform that does begin at time t equals 0, but now it's this exponential, and it's an e to the minus t in this case. So now what we're doing is, in this class, we are sticking with one-sided transforms. We're saying we're drawing the line in the sand at time t equals 0. And we will now say that all of our time, and so what I should have done here to make that explicit is I should have said for t greater than or equal to 0. That's little f of t. That's what I should have done. Does that help? So that's now the unit step that you could multiply each of these waveforms by, but you're really using the unit step as a switch in that case. Questions so far? Now what I want to do is I hope you believed the discussion that we said this should give us exponentially damped sines and cosines. And right now that's not explicitly showing itself, but it really is with those complex exponentials appearing. But we also have these phasors floating around, but how else could we write those phasors? Let me rewrite this. I now can say f of t is equal to 1/2 e to the minus t. And now let me rewrite that 1 at an angle, or 1.2 at an angle of 50. Let me write that as 1.184 e to the j 50.8 degrees. Isn't that the same? It has a magnitude of 1 and an angle of 50.8 degrees. That's e to the j 50, or e to the j 51. And now I can multiply that by this e to the minus, well, let me go ahead and pull those pieces apart a little bit and say that that's e to the minus 2t, and it's an e to the j 3t. And likewise, I can have plus 1.184 e to the minus j 50.8 degrees, e to the minus 2t, e to the minus j 3t. Again, that's valid for positive or non-negative time. Now I'm going to combine some of the exponent pieces. And you have to remember also that you may be mixing units. What are the units on that 3 in the j3t exponent? What are the units on 3? Radians per second. And the 50 is in degrees. So the 3t will be radians, and the 50.8 is degrees. So if you start calculating these numerically in your calculator, you want to make sure that you're using consistent units. Question? Yes, you're going too fast for me. The question was, isn't this just the cosine? And the answer is exactly yes. But I'm trying to show you where these formulas come from in your textbook. So they're going to show you the formula to inverse a complex set of roots is 2 times the magnitude, and then you just offset the cosine's angle by the angle of that partial fraction coefficient, and that's what's going to fall out. If we look at this now, we have this f of t is 1/2 e to the minus t plus a 1.184 e to the minus 2t And what's left is I have an e to the j 3t plus 50.8 degrees, and I have a plus e to the minus j 3t plus 50.8 degrees. And what you were just telling me before is what's inside that square bracket. That's 2 times the cosine. So this is now a 2 cosine of 3t plus 50.8 degrees. And consequently, our f of t becomes this 1/2 e to the minus t plus 2 times 1.184 e to the minus 2t cosine 3t plus 50.8 degrees. And that's true for t greater than or equal to 0. Questions on that? What are some observations we can make so that we maybe don't have to go through all of these steps in the future? One was the fact that these coefficients associated with the complex pole pairs were conjugates of each other. A sub 3 was A sub 2 star. Meaning if we have poles that are complex conjugates, all we really have to do is find one of those coefficients, and to be consistent with the textbook, which coefficient do we find? We find the coefficient associated with the pole that's in the top half of the S-plane. That was the A sub 2. Once we found A sub 2, then if we want to inverse Laplace transform this, let's say A sub 2 over S plus alpha minus J beta, that's going to have its conjugate here. And what do we know that equals? We know it's going to equal 2 times the magnitude of the coefficient for A sub 2. What's the exponent on the damping term? That's e to the minus alpha t cosine. What's the frequency of, that's the damped frequency of that cosine? Beta. And it now is going to be offset by an angle theta, where A sub 2 is this magnitude A sub 2 at an angle of theta degrees. Meaning, once you've found A sub 2, you can immediately write down the time domain expression. You don't have to go through all of those steps that we went through. That was to try to convince you that this formula is correct. You just have to find 2 times the magnitude of A sub 2 and then shift the argument of the cosine by the angle of A sub 2. And this should be in your textbook, equation 1264. And some of these are in table 3 in chapter 12. Now, well, maybe it will depend. Are you guys experts with MATLAB? All right, I'll just assume you are. No, I will maybe talk a little bit about that, but maybe that will be more offline than in here. But you can do this in MATLAB. You can do this partial fraction expansion. You can find the residues. You can use the residue function in MATLAB. And we'll maybe talk try to talk a little bit more about some of the ways that you could do this partial fraction expansion with your calculator if you have the appropriate calculator. But let's now look at case 2. Which is the case for repeated roots. If I now have capital F of s equaling, let's say, n sub 2 of s over s plus p1, let's just say squared, and then s plus p sub 3. So I'm basically assuming p sub 2 and p sub 1 are equal. So now I have s plus p1 times s plus p1 times s plus p sub 3. What's my partial fraction expansion going to look like in this case? It's going to have really the same structure as before. It's just that now the s plus p1 factor is going to have two different partial fraction terms associated with it. It will have an a1 that's associated with s plus p1 squared, and then you just start reducing the order on that factor until you get down to the power of that factor being 1. Meaning, if s plus p sub 1 was cubed, you would have an a1 over s plus p1 cubed, plus an a sub 2 over s plus p1 squared, plus an a sub 3 over s plus p1. And really all we need now are the same things. We need to find a1, a2, and a sub 3. How do you think we will find a sub 3? That hasn't changed at all, has it? That's a distinct root, and we know the formula for distinct roots. We can find that. Now a sub 3 is just going to be s plus p sub 3 times the f of s evaluated at s equal minus p sub 3. What if we tried the same formula on the other two? For a sub 1, we have s plus p1 squared f of s equaling, so that's now this n sub 2 of s over s plus p sub 3, and that's going to equal a1 plus s plus p1 a sub 2 plus s plus p1 squared a sub 3 over s plus p sub 3. Well, now a1 has been isolated just like we had before. So we can find a1. Where we're going to get tripped up is finding a sub 2. And we'll talk about how we find that on Thursday. And that's because we have repeated roots, we have to do something a little different. Make sure I get your in-class participation, which should have really stressed you as far as what it required. I simply want you to write down your calculator.